Hello, I'm Scott Lundquist. If you're like most biochemistry students, it has been at least a few semesters since your last math class. Or maybe math just isn't your thing. Math's for physicists, right? Well, today I'm going to walk you through a couple of equations commonly used in biochemistry, and by the end, you're going to feel like a math stud. Let's get started. One equation important in the field of spectroscopy relates the chromophore concentration of a solution to how much light is absorbed by the solution. This is commonly known as Beer's law. That's beer the scientist, not the malted beverage. Now before we dive in, I want to take a moment to talk about a study tip I have found very useful. Whenever I set out to learn something new, I try to find a unique or quirky way to make it stick in my mind. These funny tactics are more commonly known as mnemonic devices. So, while you are reviewing these equations today, use a mnemonic. And remember, all mnemonics are not created equal. Use a mnemonic that you will remember. Let me give you an example. Absorbance is defined as being the log of the ratio of incident light to transmitted light. Ugh, how am I supposed to remember that? Well, in my mind, I imagine a log. Then I imagine an eye going into the top of the log and coming out of the other side a different color. This picture is easier to remember than a bunch of letters, and it tells me both what it means and how to write it mathematically. Voila! If you'd like, you can pause the video and practice making one of your own. Before I show you the actual equation, let's review some of the variables associated with Beer's law. A is the absorbance. We've seen this one already. C represents the chromophore concentration of the solution for which you will be measuring the absorbance. L, the path length, is the length the light traverses across the solution. Epsilon is a constant known as the absorption coefficient. Finally, lambda is the wavelength of light incident on the solution. Now let's take a look at Beer's law. Beer's law is a linear equation, meaning that the absorption is linearly dependent on the chromophore concentration, or alternatively, on the path length. In other words, if you plot absorption against chromophore concentration, you will get a straight line. Okay, so here's a question about plots. Based on Beer's law, what would the slope of the line be for this equation? If you're thinking the absorption coefficient times the path length, you'd be correct. Okay, one more thing before some examples and practice questions. You are probably wondering why we haven't used the wavelength, which we defined earlier. Well, we actually have, and this is how we represent that. Writing the equation like this tells us that it has a specific absorbance and absorption coefficient for different wavelengths. Okay, let's look at an example of how you might use Beer's law. Let's say you dilute 275 microliters of a 0.01 millimolar stock solution of some chromophore with 725 microliters of a buffer in a 1 centimeter by 1 centimeter cuvette. You measure the absorbance at 520 nanometers to be 0.5. What is the extinction coefficient at 520 nanometers? Remember that extinction coefficient is the same as absorption coefficient. Let's take a step back for a moment. What if I had asked about the extinction coefficient at 430 nanometers? Your answer should be that I have no clue. That is because we don't know the absorbance at 430 nanometers. Okay, just checking you. Let's write out Beer's law now. The first step is going to be to isolate the desired variable. A lot of people will make the mistake of plugging the numbers in right away. Rather, solve the equation analytically first, and then plug the numbers in. Trust me when I say it's less messy that way. Now that we have solved for the extinction coefficient, we can plug in our variables. Note here that I've already used C1V1 to solve for the chromophore concentration. When you have finished calculating the answer, check your units. This is a good way to know if you are close to the right answer. The extinction coefficient should have units of 1 over a length times the concentration. Now go ahead and pause the video and try a few practice problems on your own. Welcome back! Now that we've mastered Beer's law, let's try a hand at the Michaelis-Menten equation and Lin-Weaver-Burk plots. Like before, let's review some of the variables. Michaelis-Menten is an equation that tells us about the rate of an enzymatic reaction. E represents the enzyme or enzyme concentration. S is the substrate or substrate concentration. ES represents the enzyme substrate complex, and P represents the product. Lowercase k with a subscript represents the rate constants for forward and reverse reactions. V sub I is the initial rate of the reaction. Vmax is the maximum reaction rate, and Km is the Michaelis constant. Now you won't need to know all these variables to solve the equation, however they are useful while working on enzyme kinetics. The Michaelis-Menten equation tells us that the initial speed of a reaction is equal to the maximum speed of the reaction times the substrate concentration, all over the Michaelis constant, plus the substrate concentration. The question becomes, How do we figure out what Vmax and Km are so that we can determine the initial speed? The answer is experimentally. To figure out these constants, start by measuring the velocity of a reaction at several substrate concentrations. Then create a plot of the velocity of the reaction versus the substrate concentration. You should get a graph that looks something like this. The shape is called a rectangular hyperbola. At this point, you've probably started to notice a problem. Sure, we could estimate Vmax by finding the asymptote of the graph, but how the heck can we determine Km? Well, other scientists also noticed this problem, and a couple of guys named Lundquist and Burke figured it out. Lundquist and Burke figured out that by using a double reciprocal plot, they could determine Km and Vmax directly. To make this plot, you plot the inverse of the speed versus the inverse of the concentration. This should create a straight line. The y-intercept is the inverse of the Vmax, and the x-intercept of this line is the negative inverse of Km. Okay, let's look at an example. Let's say we performed a series of assays and have the following results for substrate concentration and initial velocity. The first step is to create two new columns on your table, one for the inverse of the substrate concentration and another for the inverse of the initial velocity. Next, plot these values. If you use Excel or another spreadsheet program, you can have the computer spit out the equation of the line for you. I recommend this method mostly because it saves time and it's more accurate than doing it by hand. The y-intercept will be the b in the y equals mx plus b linear equation the computer displays. To find the x-intercept, set y equal to 0 and solve for x. Remember, doing it analytically first is less messy. Once you have these values, take the appropriate inverse or negative inverse, and there you have your Km and Vmax. Now take a moment to try these practice problems. Okay, now that you are experts on Beer's law and the Michaelis-Menten equation, let's review. Beer's law tells us the absorbance of a solution containing chromophores given the path length and extinction coefficient. Remember, absorption and the extinction coefficient are wavelength specific. To determine the Vmax and Km of the Michaelis-Menten equation, experimentally measure the initial velocity for several substrate concentrations, make a double reciprocal plot, and use the inverse and negative inverse of the y-intercept and x-intercept to find Vmax and Km. This concludes the review. Now go and do good science.
This presentation was brought to you by Jedi Knight and Scott Lundquist. Copyright 2012, all rights reserved.